thank you all for coming to my talk. So today I'm going to talk about how you can sandbox a Linux application. If you have a question at any point in time, just feel free to stop me and ask. It's better for me to skip a couple of slides than you not getting your answer. So feel free to interrupt. So I'm Martin. I work for Cisco. And well, the last few years I've been working more and more in the systems programming and security field on our embedded devices. And so sandboxing ends up being quite a nice little corner where these two things meet. So I've dug into that and probably doing more of that than I should have the last few years. But for some reason I find it fun. Yeah. Before I begin showing you any code, so today we're going to actually make a sandbox. Do not use this sandbox. It is horrible. The code on this slide is not meant for anything but being on slides. I, for instance, don't do error checking because then the code won't fit in the slide. And if you don't do error checking on your sandbox, then it will just run through and you will think you might be sandboxed, but you're not, and everything will be horrible. So don't do that. I will take no responsibility if you do this. You should actually not write your own sandbox. You should use one of the ones already invented for you, but it's fun. Now, one thing we need to look into is, like, what do I mean when I say sandbox? Like, what's the purpose of a sandbox? Why do they even exist? And I Googled around quite a bit. And I ended up with something like this. Basically, it's a mechanism to limit the view of an application. So you put an application into a restricted and controlled environment that you restrict and control. And the goal of it is not to make shitty code better, but it's to constrain the shitty code so that it can't affect anything outside of it. So you want to limit the impact of the vulnerabilities. You can't really stop them, but you can limit them. Like I said, I Googled around. I didn't really find much, so this is my quote. But I was kind of happy-ish with it. And now we know what I mean when I say a sandbox. The question becomes, why would you use one of these? And there's a couple of them. There's a couple of reasons. Like I said, I work on embedded devices. Sometimes you might get an application from a third-party vendor that you don't really trust. You don't really know what it does because all you get is some binary blob. So you want to restrict it to do just the thing it needs to do and nothing else. You might download code from the internet and run it locally, which sounds insane to do, but we all do it every day because this is how a web engine works, right? And web engines are heavily sandboxed. You might have an application that has some expectation of the environment it's running on. For instance, it might expect some files to exist somewhere on the system, and on your system, it's not in that place, it's somewhere else. It might be so easy as /lib, is that 32 or 64-bit? You could, of course, like rewrite symbolic links and mess around or change your system. But you could also do kind of what Docker does and just rewrite the file system and the environment so that it looks like the application wants it to. And of course, they're really fun, which is not a good reason to write them, as I said, but it's a very good reason to actually learn about them. And there's quite a few tools on Linux for actually making a sandbox and that you need to use to make a sandbox. So today I'm going to talk about the first two, namespaces and Seccomp. C groups I don't really have time for. If you want to learn more about C groups, go back in time and watch Michael's talk, or watch it on YouTube when it's out. He also had one in NDC Tech Town in last year, which goes directly into C groups. But these are all basic building blocks that every sandbox and every container environment is using to constrain the application they're running. Let's get to some code. And there's a couple of ways you can set up a sandbox, that you can start a sandbox. And in the initial version of my talk, this is what I did. Basically did some setup, and then I exec the next argument. So I could run it like sandbox, application, and arguments. This is what I did for the first one. What happens then is that you need to have some more things mounted. You need access to a bit more things, because when you start up a program, you need some libraries, for instance. That needs to be loaded. So those would then need to be mounted into your sandbox, which could and could not be fine, depending on how paranoid you are. What you couldn't do with this is to completely remove yourself from the file system. If you don't need the file system, you might want to consider just removing it completely. So you could do something like this. Basically put the sandbox inside of the application. Set up the sandbox, run the application code. Then you can remove yourself completely from the environment. Of course, if we go back to my first point about why do sandboxing, you have some binary blobs you don't trust. You can't edit the binary blobs. So instead, we go ahead and do something really nasty. This is the equivalent. Basically, I can start by showing you how this works. So I have this application. It doesn't really do much interesting stuff except find lots of information of the device. So it's like you find UID, GID, PID, what directories are in the root directory, and all the PIDs, network interfaces, capabilities, and such. So how to run this sandbox is, let's get this on top. You do ld preload. So lib, and there's a shared library, which is the sandbox. And what ld preload does is it takes this library, and then every public symbol in this library can be used to override public symbols from other libraries that you pull in. So if I then run result bin application, looks very similar, except at the top, my SO file added the print running sandboxed. So the symbol I'm overriding, and this is the very nasty part, is this. libc start main, which is part of glibc. You don't know if this changes, by the way. So when you upgrade glibc, this might break. But then there's other stuff in your sandbox that might break by a glibc upgrade anyway. They are finicky. So what I do is I store whatever the actual main of the program is into a variable. I find the actual libc start main because I need to use it. The linker needs to do its job. And then I call that libc start main with my own main function. And currently, my own main function only calls actual main, which is the one I stored. But between these two lines, I'm going to put my sandbox. And we'll start by namespaces. So namespaces are a way to wrap some global system resource like PIDs and mount points, network, APC mechanisms, users. And when you boot up, everything is starting in some initial namespaces, one of each type of namespace that we have. We are going to use the unshare system call to make them. You could use clone, but clone is way more complicated, so I'm not going to start with that. We're going to use unshare, which is a simple way of creating and most of the time entering a namespace. And we'll start with the user namespace, which isolates user and groups. Basically what it does is you can map the users and groups you have available to users and group in the parent namespace. To enter it, you use this clone new user flag, which you give to unshare. The most important thing here is that when you do this, you can pretend you're root. You can basically get root-ish permissions. So in this world with namespaces and user namespaces, root isn't really root anymore. Looks like you have privileges, you might not. So you have this initial namespace here, where you're running as user 1000 and group 1000, and you create a new one. This was very, well, namespace 2 in this case, and you have these mappings. These mappings are two files, UID map and GID map. So the first one is the user ID map, where you say that UID 0 inside of the namespace is UID 1000 outside of it, and you do that for a single user. Which means if you as user 1001 enters this namespace, you'll be running as nobody, because there is no mapping for your user. You can do more fancy mappings like this, where you map 500 users starting from 100 inside the namespace and map them to 688 outside of it. And you do a similar mapping for the group IDs, which ends up with something like this if my math isn't completely off. For Docker, for instance, the default mapping is the identity mapping. So 0 is mapped to 0 for all the users, both for user and groups, meaning in Docker, if your Docker container is running as root and you haven't done anything to change that mapping, then it's actually running as the true root. But this is how you create and join a user namespace. It's pretty simple. At this point, you're running as nobody. At this point, I think you have 0 permissions. But let's make ourselves root. Let's write to these files. So the files we need to write to is this UID map, and this GID map. So you fetch the user ID and group ID before you enter the namespace. You enter the namespace, and then you write the mapping to these files. You write 0, whatever your outside UID was, and you do that for a single user. And you do the same for the group ID map. And this is the point where you should have checked errors, because this last write will fail for you. Because you're not allowed to just write to this group ID map, because on Linux you have the capabilities of adding new groups to yourself, especially as root. So before that you have to deny the kernel giving you supplementary groups, which is done by this. You write the string deny to proc self set groups. Now proc self is magic. It's basically proc your PID, whatever that is, / set groups. But you have to write this string deny to this file to be allowed to write this mapping. And after doing this mapping, we'll be running as what looks like true root. We'll have every capability, and I'll show you a bit later in a demo how this will actually end up looking. Now the reason for starting with the user namespace and doing a very high-level explanation of it is that you need permissions to enter any other namespace, except for the ones that your user namespace owns. So you can create a lot of them together if one of them is a user namespace, and you can do that unprivileged. If I didn't do this first, my program needed to run as root to begin with, which kind of makes the whole thing worse. So I start with the user namespace. And the next thing I want to do is make myself a new file system. I could remove myself from the file system. Let's start by making a new one. And we do that using the mount namespace, which gives you a new list of mount points for, well, your namespace. This flag, clone UNS, clone your namespace, is what you use for this. You can love or hate the name. It's the first namespace ever created, and as always, you think this is also going to be the only namespace ever created, so you take the most obvious name. You can share your view of the mount points with the namespace your parent is in, or you created it from. Previously, the default was that when you created a new mount namespace, the new mount namespace were private. Every change you did was private to you. Systemd changed that default to actually share them. So if you did a change in the namespace, that change was also shown in the previous namespace, which in this case would be pretty bad, and vice versa. So basically, if you don't know what init system is running, you don't know what the default is, so you should just always make sure to start with, make every mount point private. Like I said, it's easy to make and join a new mount namespace. You just OR the flag in. At this point, the one you had and the one you're in looks exactly the same. There's no difference. So, like I said, you have to make your mount points private. And the way to do that is by, on top of /, which is your root, make that private recursively. It's basically what this line is doing. So after this, any change you do to your mount point list is yours. So at this point, let's make ourselves a new root file system. What I do here is I mount a temporary file system on top of /temp. So whatever was in /temp is still there, but I mounted a tempfs on top of it. Basically because this is where I want to create my new root file system, my new /. And I use temp because there's most likely nothing in temp I need to copy over. And I'm pretty certain that temp will exist. If not, you would have to create it, or create a directory somewhere to make your file system. To basically bring stuff over from your old mount file system to your new, you create a directory or a file. You can do this with files as well. And then you do a bind mount from the old one, lib64, to my new root file system's temp lib64. This basically makes a copy of the mount point that is now pointing into something inside of what your new root file system is. And here you can mount up as much as you want to. You can mount other type of file system. You can mount a squashfs or whatever you want to mount. And nothing of this is seen by the parent. So now I made myself a nice little file structure under temp. So I want to join it. Now you could use the good old chroot. The problem with chroot is that that would impose on your application the restriction that it cannot join any new user namespaces. That might not matter for you, but if you want it to matter for you, you have to use pivotroot instead. And pivotroot works that it takes two arguments. It takes whatever the new root is supposed to be, and it takes where to put the old root. After doing this, whatever was in /temp is now in /. Whatever was in / is now in /old root. Then you cd to your new /, because if you don't, then you're still wherever you were, which I have no control over, so I cd to the new /. Then you unmount the old root and remove the directory, and the old file system is gone. as far as at least your applications will see. So you built up a new file system, you entered it, and now you're locked into that part of the file system. One thing you couldn't do at this point, so at this point my application would crash because it lists all the PIDs that exists, and it does that using the proc file system. And you cannot mount a new proc file system here because there's already one mounted in your PID namespace. So the next part is to make a new PID namespace. And these are interesting. The first thing you'll notice is that when you use unshare clone new PID, you create it, but your process is not part of that PID namespace. The reason being that if it did, then for instance, dlibc could no longer just cache the PID. It would need changes on the user space side if they did that change, and that's not something the kernel is very happy to do. So the rule is the first child of this process will be the first process in the new PID namespace. Also, this process will be PID1. And PID1 on Linux is the init process. It's kind of important. Like some of what it does is create other processes, which is less important in this setting, I think. But it also becomes the parent of every orphan child process, which is an important task it has. What a PID namespace does is it basically starts counting PIDs again. Very easily told. But a PID in an other PID namespace also has a PID in the parent PID namespace. So the parent here, this init PID, init program, will see this application as PID 3451, but this will only see itself as one. And here, this one will see the process in namespace 3 as PID2, while it's actually in the initial PID namespace 1024. So there's a hierarchy here with mappings from whatever it sees itself as to whatever the parent namespace sees it as. And all of these PID1s are considered an init system. So if PID1 dies in a namespace, that namespace is shut down. And this is also why in Docker, you're recommended to have a single application inside of your Docker container, because if not, the first application needs to be an init system or an init application. Because that's the requirement. It has to work as an init system. Now, to create it, it's very easy. Same as always. The difference now is when I do the set UID GID mapping, I am in a new user namespace, I'm in a new mount namespace, but I'm still in the initial PID namespace, or the parent PID namespace of the one I created. So to enter it, I need to create a child, which I do with fork. If I use clone here, then the child will be the one that's been put in the PID namespace. So use fork, and I do the swap root thing, and I call actual main, and I exit. In the parent, I then wait for the child to terminate, and I use that as the exit status. If I didn't do this in the parent, then I would send a sig kill to the child, and nothing would really work. But this would get me a completely new, this will create a child that is also part of the new PID namespace. So this child will be PID1, and it will see no other processes. The other thing I can do now is mount my proc file system. because now I'm in a PID namespace. I can now mount my own proc file system, so I do that. And the last thing we're going to do, namespace-wise, is remove ourselves from the network. In this application, my application don't need network access at all. And a network namespace will create a new networking stack. It will have its own set of Ethernet devices or network devices. It will have its own IP table set up. You can do whatever in this. On creation of a new network namespace, there exists only a loopback device, which is down even. So it's very shut down. And a network device can be present in a single network namespace. You can move even physical devices into other network namespaces. Or you can make virtual Ethernet devices that you put into, for instance, a virtual Ethernet pair where you put one side of the link into the network namespace and the other one is in the initial one, and then you can do some IP tables magic and get actual network. Not going to go into that because IP tables is a nightmare to work with. But if you exit a network namespace that has network devices, the virtual devices will be deleted and the physical devices will be moved back to the initial network namespace. And these are not hierarchical, they are just side by side. So I could move ETH0 here into this network namespace. And if I wanted to, I could move it further into this one. But then if this one dies, it gets moved back to the initial network because ETH0 is a physical network device in this scenario. Yeah?
When you move a physical network device into another namespace, it disappears from the initial namespace?
Yes. It can only be in a single namespace at one time.
So any active stuff that was happening on that network interface?
Gone.
So it's basically like you ripped the PCI card out of the PC?
Yeah, basically, for the applications, I guess it would look something like that. I haven't actually tried that, but yeah, it can't be active in two namespaces at the same time. And also, all of these loopback devices are separate. So if you have some services running on your local host in one network namespace, they will not be accessible from another one.
I think that situation rarely arises in practice because the physical devices are always kept in the initial namespace.
What you regularly do is you have something like this in the initial namespace, then you put a virtual Ethernet pair between two namespaces, and IP table magics on this side, or a bridge device or something like that to actually route it out. Yeah, I haven't seen any use where someone actually moves the physical network device, but you could. So to create a new network namespace, as we always do, unshare clone newnet. This is done in the child. The idea behind doing it in the child in this case is that if I did this from the parent, I could, if that had the privileges, start setting up the network devices properly, send the network device into the network namespace and signal that everything's ready. Of course, I don't do that because, like I said, IP tables, I've done too much about that and I'm not really, I don't have time to do all of that. So basically what this does is it just removes the network from the application. And yeah, you can use virtual network devices. You need to use IP tables. Bridges will probably help you a bit if you want to go through the pain of actually getting network. So if let's just get there and build it. Now the application is unchanged in this. It still does a lot of stuff. But if I run this with LD preload, there's a lot less information here. So you see I'm running as something that looks like root. And I'm PID1. I have every capability. I have no network interfaces. I have some directories mounted. Those are stuff I just mounted out because to show it. I could have removed everything in this. And I have one running process, which is myself. So with namespaces, you can basically remove yourself from the machine, or take an application and remove it from the machine. The main usage here is not to protect that application, but protect the rest of the system. You have many more namespaces. And for a proper sandbox, you should at least consider all of them. For instance, kernel IPC mechanism is probably something you don't necessarily want between these namespaces. But there's if you're making a proper sandbox, you should consider all of them. So we go to the next part. And the next part of this equation is Seccomp. And if you use Seccomp, you're allowed to do the system calls exit, sig return, read and write, which is very, very useless for most applications. If you have a very limited application, you might be able to use this. But instead, we use something more modern, Seccomp BPF. So when you hear the word Seccomp, this is probably what people are meaning. This is what you're actually using. It uses the Berkeley packet filtering, which is infrastructure in the kernel with VM, JIT compiler. It's a binary programming language. And it's pretty powerful. You use it to deny or allow syscalls. So you're always working on syscalls in this. So the thought behind it is you have an application which does some things. And those things require certain syscalls to be made. There's a ton of syscalls. Michael said about 400 or something these days. Your application probably uses a handful of those. Compared to how many there are, you're not using many. So you want to limit your application and anything inheriting from application, so any child process made by your application, to only be allowed to use the syscalls you're actually using. So if an attacker comes in, hijacks your application, they can only trigger the syscalls you're already making, which limits the attack surface quite a bit. The one thing you need to remember to do when doing Seccomp is that you need to check that you're on the architecture you expect to be on. So if you're running on ARM64, you should check in your BPF program if you're actually running on ARM64. Your BPF program is written for ARM64. Not because the binary code is different, but because the syscall numbers differs. The syscalls on ARM and ARM64 and x86 and x86-64 all differ. Now you have a struct that you work on with Seccomp. You have the syscall number at the top. You have the architecture you're running on. You have the instruction pointer, which I think is really cool, but I haven't seen any proper use of it. But in theory, you could say, I just want this syscall in this region of code. And you have pointer to arguments for this syscall. And I'm going to start, because I have time, by using what I call a raw Seccomp, which is basically the kernel interface you have for making Seccomp. But I would prefer to use libsecomp, so we'll do that afterwards, because that's much nicer. This is going to be hairy, as you see from the get-go here. Okay. To make a Seccomp program, you create this sock filter thing, which is your program. You put it into a sock fprog, and you send it to Seccomp. And this filter contains statements and jump instructions, basically. So this one is a statement, and all it says is return allow. So you allow every single system call. This is basically what you have as default. So let's expand on it. And let's check the architecture. Like I said, that's important, so let's do it. So what you do for that is you load from this Seccomp data struct the architecture. So you load a word from the Seccomp data structure into a register. And this offset of thing is just the way to get actually where in memory this thing is stored. When you load that into a register, you can do a jump statement. And you say, I want to jump if the following is equal. And the following is arch x86-64. If whatever's in the register is equal to arch x86-64, I jump 0, meaning I go to ret allow. And if not, I jump 1, jumping over this statement, hitting this one, going to ret kill. I said I was checking the architecture here, and I'm trying to check x86-64. But this is pretty nasty. And this is not even a full check. Because I'm not checking the x32-bit in this, which you should do, and I'm not going to do because I'm lazy. But this is not a full architecture check for x86-64. Don't use this code. If I want to check actual system calls, I kind of do much of the same things. I do a new BPF statement where I load a word from Seccomp data, this time the syscall number. So after doing the architecture check, I don't care about the architecture anymore. I load in the syscall number, and I check if that syscall number is equal to sysexecve. If it is, I jump 0, going to allow. If not, I go to kill. It's pretty much the same thing. What you also see, I have to update this jump. Try and hit it there. This now also have to jump over these two new instructions. Because I want to jump to kill. And if I don't jump far enough, I would end up just checking if whatever is in the register would be the same as sysexecve, which is not interesting for me at all. And would be, well, it would be very interesting to see what happens. And we end up with a lot of these BPF jump statements. And this is not very nice to maintain. This is a very, very small BPF program. You saw what the program did. It does nothing. And at some point, it's going to do more. For instance, when you update glibc. So you need to add a new syscall into this list. So you can add it at the bottom. If you add it at the bottom, every single jump on top of it needs to be changed to accommodate for the new statement. You could also add it at the top, like just after the architecture check. Then you only have to change and jump for the architecture check. But if that's a statement, if that's a syscall you only do once, and this receive message is something you do 100 times a second, then you will have to evaluate that new syscall that you only use once for every time you actually need to do receive message. Ordering here matters. You want to have the ones you actually use frequently at the top. And you're gonna mess this up. And if you don't mess this up, one of your coworkers are gonna mess this up. And we haven't even looked at checking arguments yet. So checking new arguments creates the same issue. So what you do for checking arguments is in this very dumb scenario, I check if the exit code I'm sending back is 0. So I only accept that we exit with a success. If not, I kill the program, which is idiotic, but it illustrates the point. So you check if it's exit group. If it is this syscall that you want to check the argument for, you just continue. And if not, you jump over the argument checking phase. So when you do the argument checking, you have to load, just as we saw with loading the syscall number and the architecture, you have to load whatever argument you want to check into the register. In this case, it's just the first argument. And then you can compare that the same way that you did regardless. You check if the exit group was 0. If it is, you jump 22, which I hope hits allow. We'll see when it runs, hopefully. And if it's not, then we jump to 23, which hopefully is kill or some error handling thing. Now, at this point, you know you're at the syscall exit group, which means you should always jump at this point. Like, you can do multiple argument checks. You can check if it's in a range or a set of things or whatever. But if the syscall number is exit group, you should never check if it's sent to, because why would you? Like I said, this is going to be complicated to maintain. It's going to break at certain intervals. So instead, let's introduce libseccomp. Libseccomp is a library that basically helps you write these seccomp filters. And the way to do it is you create a seccomp filter and you give it an action, which is the default action. Basically, you're telling seccomp, if no other rule has come in, kill the program. So this is basically the same as the bottom one here. If nothing else happens, jump to whatever this seccomp ret kill is. Then you do seccomp load to load that program into the kernel. That creates the binary application, puts it into the kernel. At this point, you don't need it on the host side anymore, so you release it. That's just user space memory. One big difference between these 3 lines and the, I'm not sure, 8 or something that we had for setting up the initial raw seccomp, this does the architecture check for you. And it does it properly compared to what I did. So this is a step up. If you want to check a syscall with libseccomp, you add a rule to the context you created, and you say, I want to allow, SCMP act allow, execve. And you have 0 cares for argument at this point. We'll come back to this 0. Now, SCMP sys also goes ahead and makes sure you get the correct syscall number, depending on the architecture, because you could be cross-compiling and then libseccomp will take care of that for you. You also see here, because at some point I actually added some architecture changing code. This is how you set an architecture for libseccomp. Now this is a lot nicer than doing the exact same thing in raw seccomp. And we end up with something like this. Here I basically just wrapped the seccomp rule add into allow libseccomp, because all of these do the same thing. Add it to the context with allow and 0 arguments. It is very repetitive. It's not like this is interesting code to write. It has to be written, but it's really boring. But the nice thing about this is I can reorder this as much as I want to, and no jumps will fail. Neither me nor your coworker will break the sandbox if you just rearrange some stuff here or add a new syscall. If I want to check arguments with, yeah.
So you still need to know about the syscall numbers, I assume. Those,
No.
Those names there, are those glibc functions or are they syscalls?
They are syscalls.
Yeah. So you still need to know that, say, if I call this glibc function, it actually maps down to this other syscall.
Yes, that you need to do. I'll show you actually how to find the syscall number when I do the demo of this afterwards. Because yeah, you need to figure out what syscalls you're using, and to do that is, well, you get a list of numbers, and then you need to figure out, because you could write the number directly here, but that would be horrible to maintain again. So you need to find out what system call this syscall number on your architecture corresponds to. Now, if we want to check arguments, this is where this 0 comes in. That 0 means we have 0 argument checks. This 1 means I have 1 argument check. I can have multiple argument checks for the same argument. So what I say here is, for argument 0, the first argument, I want to check if that is equal to 0. So this is, with libsecomp, it's very easy to check like a range, because you can check if argument 0 is less than something, and then check if argument 0 is bigger than something. It's fairly trivial. You just add 2 of these SCMP A0 and then change number 1 to 2, and then you're good. Now, one thing that came up for me when I was doing this is that a lot of these syscalls, they don't take numbers. They take a string or a path or something. So how do I compare strings? There are probably many technical reasons for why you can't. But the reason why you cannot write something that dereferences a string is that you don't have the string value. It's not copied to the kernel at the point Seccomp runs. So what you could do, if you really, really want to check these strings, you can have a static, which has its own memory location that you use all over your program, and you compare the memory location you get to libsecomp with, or just to Seccomp, with that memory location. Of course, if someone writes the same string and it's not using the same static memory, then they will fail. That won't be allowed. But generally, just there's no real reason to. So let's see how libsecomp works. So in this one, I'm actually running libsecomp as well. This is not an exciting demo at all, because it just doesn't do anything. So let's go in and change that. So I have this file. And let's just remove one of these. CapGet. I don't need CapGet anymore. So I now remove the line. I build it, which takes some time, but not too much time, luckily, and I run it again. And as you see, when I try to get the capabilities, let's just get this a bit up, I crash. See, the exit code is 159. Because I removed that line, I can no longer run this program because it's using a system call that is not allowed. Now, Johan asked, how do you figure out which system calls you're actually using? If you have an audit log on your system, then that's where that comes up. Or you could just check here. I'll just do. So you see, I have a audit entry in my logs. It tells me that this application, don't care about the whole path, it's Nix stuff. It gives me the actual UID and group ID I'm running as, the one from the initial namespace, because the kernel doesn't care at this point. And you see, it got a signal 31. This is the architecture I'm running on, and this is the system call. So what you could do is you could take this system call, copy paste it into your application, just use the number 125, but you would have no idea what system call that was. Other thing you could do is Google, which I did. You could go in and Google. I'm not sure, do you have any tools for actually getting from the system call number to the system call?
I use syscall.
Syscall.
I use syscall.
Are you?
AU.
AU.
Syscall.
I don't have that.
Oh, so yes.
Let's maybe no. Okay, I don't have that.
It does the translation in either direction.
Okay.
There's another tool as well that does the same translation, but I forget what its name is.
Okay. Yeah. So what Michael said, you could use this tool, AU syscall. I don't have it installed. Not gonna find out what it's actually named in Nix. But you could use that to get from the system call number to the system call name, and vice versa. And while developing this, you should probably set it not to kill. You can set Seccomp to allow everything but log errors. So Seccomp ret kill would end up in one audit log entry. So if you did that, you put in a Seccomp program which just says kill everything. You run it with what's the name of it again? It's this one should be Seccomp act log, I think. Then you have one entry for every time a system call is called and denied. So you would get every single system call your application uses in the path you're running. For complex programs, this is very complex, but it will get at least the paths you're actually taking. And it's kind of, you have to use the audit log or the logs because you don't really know what system calls glibc does for you. Just as simple as looking at, this is far back, when I make the PID namespace, I do fork. Fork is a system call, but the glibc fork function doesn't use fork, it uses clone. So you would have to add clone and not fork, even though it looks like you should add fork. And there are multiple of these. Open uses openat. It's, yeah. So use those tools to figure out what system calls you're actually using. If you use the log, you will also see which system calls you're using a lot, because they will spam the log. Now there are other tools you should consider. C groups, I don't have time for today, but Michael both talked about it earlier today and had a full talk on it on NDC TechTown last year. Go and watch that. SLinux as well. There's some overlap between SLinux and Seccomp, but they can, like, SLinux also does other stuff, and they don't interfere with each other. And yeah, that's all I have. Any questions? Yes?
Yes, so Michael spoke earlier today, and he said that processes or child processes do not inherit the Seccomp filters. You said they do. What is the case?
I don't think I said that, because that's
Okay.
Yeah.
certainly not what I meant.
No.
That's good.
Child processes do inherit.
Yeah.
Okay. So is this does Docker do something like this? Does it?
Docker uses all of this and more.
So you have this add cap add capabilities for Docker.
Mm.
Take care of all that.
Yeah, so that's
Default in Docker, are they okay? So you generally don't have to add your own Seccomp filters to applications running in Docker?
generally you don't have to if you're not insane and try to, for instance, Dockerize Chrome. Chrome is a beast. Someone's done this and added their own Seccomp filter to Docker to be able to containerize Chrome. It's messy. In some cases you have to, but now I have the let's just fix this so I can run my program again. No. Next build. The capabilities are these. And I should have mentioned, you get all capabilities here, but you should drop the ones you don't need. The capabilities the program doesn't need should be dropped. And what Docker does is it does all of this, and you end up with this capability set. And then you use the cap thing API for Docker to drop the capabilities, or just keep the capabilities you need, not everything. Yes?
So say I write a Seccomp filter for my application, but then I also run my application inside Docker. So Docker presumably also adds Seccomp filters.
Yes.
Are those combined in some way, or does the system disallow one when the other is in place?
You can restrict yourself further. You can create a new Seccomp filter, add it, that narrows you down, but you can't add one that expands your access. I'm not sure what the rules are for.
There are multiple things to a process, and they all get executed. And the most restrictive action is the one that is performed. So
Yeah.
one of the fields says kill, that's it.
Like Michael said, just to repeat it for the ones on the stream or watching it later, you can add multiple Seccomp filters and they will all be run, so you will be at the most restricted Seccomp rules for child processes. More questions?
Is this code on GitHub by chance?
Yes, but it's not unlocked yet, but I will.
Okay.
I'll send a link into the Slack.
Okay. Yes.
There was a... Okay. So yeah, I'll make the code available and post it on Slack so everyone has access to it. Yes?
So one more question about glibc functions and mapping to syscalls.
Yeah.
Because I assume that in all scenarios you're not even controlling which glibc you're running on.
Correct.
You're just shipping a generic Linux application. It will run using the glibc of whatever distro it ends up running on.
Yeah.
So in that case, you're not even sure what syscall might be actually used when your application runs.
Yeah.
So the syscall numbers you would need to add to your Seccomp filter is not necessarily the ones that are actually used on your system. It might be something else on a different system.
Yeah.
So how do you figure all of that out?
Yeah. So to try and repeat the question, as an application developer, you don't control what glibc version you're running on. And glibc does a mapping from the glibc function to actual syscalls. And like I said, that might break when you upgrade glibc. So how do you make a Seccomp filter that basically caters for upgrading glibc without breaking all the time? The way I see it, you have two options. One of them is to make a wider Seccomp filter that hopefully catches whatever you need. And the other one is to go back to this LD preload thing. Because this LD preload thing could be either made specifically for your glibc version that that enables whatever this application needs, or it might be more fancy. Because, okay, let's do this. Oh, this. The thing I did was I hijacked the main, hijacked main basically, which means this sandbox can do whatever it wants to. So it can take arguments. So you can make it more generic. You can make a libsandbox.so that is more generic, that basically takes its own set of arguments, swallows those, and uses those to set up a filter that is specific to even this machine. So this libsandbox.so doesn't have to be specific to the application as mine is here. It can do whatever it wants, so it can be very configurable, and you can configure it that way. So that way, it's the way you start the application that decides how it's narrowed down.
Just to say one other thing to your question, Johan. What I say to people is your BPF filter is just like any other code that you write. It needs to have unit tests, it needs to be part of your continuous integration testing, so that if you do that upgrade, you find out about the break. It's not a piece of code you write once and forget.
Yeah. Another thing though is that since this libsandbox is basically generic code that runs in front of your main, it would be really nice if you could introspect on glibc and ask it, like, if I call open, which syscall would you use? And then dynamically create your BPF filter from whatever glibc tells you, or what syscalls to use, I guess.
That's not possible.
So a comment from Michael is you could also, like, these BPF programs are not write-only things. They're alive. You should have unit tests for them. You should make sure they're up to date so that when you upgrade your glibc, your unit test will catch that. And then you fix that. Any other questions? Okay, and thank you.